Today is November 28th, 2011, and this is AP Statistics at Berkeley High School, starting Chapter 7, having to do with sampling distributions. Chapter 7 is made up of 3 sections. Today we'll introduce the idea, actually today and tomorrow, because we're not going to be able to complete this lecture in one shot. Today we will introduce the idea of a sampling distribution, and then in 7.2 and 7.3 we will look particularly at the distribution of sample proportions in 7.2 and then the distribution of sample means in 7.3. So let's get started on what we're going to learn. In today's lesson we're going to okay. All right. We're going to learn the difference between a parameter and a statistic. We will define what we mean by a sampling distribution. We will talk about the difference between a population distribution, a sampling distribution, and a distribution of sample data. Okay? We will try to talk about what do we mean if a statistic is unbiased. And then lastly, we will talk about the relationship between sample size and variability within a sampling distribution. All right, so let's get the big picture started. I have been talking about so often that you may have it ingrained in your head that in statistics we spend a lot of time doing this, looking at a sample in order to infer information about a population. We don't have the ability to look at everything in a population. Now you say, well, sure we can. We do this every 10 years in the United States. We do a census. But I'm going to say something like, okay, I would like you to look at every single tree on one of the every single leaf on one of the trees in the courtyard, and measure every single one of them. That sounds really difficult to do in my mind. Making sure that no leaf escapes detection. You capture every single one of them. Oh, make sure no leaf from another tree ends up in your collection. So even in a really well-defined area, getting a population, a measurement of everything in a population is really, really hard. And because it's really hard, next to impossible in some cases, we got to have a reasonable technique of dealing with that. And that reasonable technique is called sampling. But there's a problem with sampling. Sampling yields different results with different samples. For example, if I flip a coin 100 times and I count up the number of heads, that is a sample of all possible coin flips. And when I flip a coin 100 times and take a sample of all possible coin flips, do I expect that I'm always going to get exactly 50 heads out of those 100 flips? No. Sometimes I get 100, sometimes I get 50, sometimes I get 51, sometimes I get 49, sometimes I get really far away from 50. By pure chance alone, I might get an extreme number of heads. And that's okay. That's called sampling variability. It just happens. If I take a sample of students at Berkeley High School, do I expect if I ask the question, oh, I'm thinking of a good question to ask. I can ask every student at Berkeley High School. Do you think we should wear hats or be able to wear hats in school? That was in the Spectator, wasn't it, this past week? Do you think that every single sample will answer that question exactly the same way? Is there universal support for wearing hats in school? Probably not. Is there universal condemnation to wearing hats in school? Definitely not. So every sample I do is going to be slightly different than the sample before. Or can be. So when we do sampling, we don't get the exact number. can think of the thing that we get out of the sample, the statistic that we get out of a sample, as a random variable. You never know exactly what you're going to get. But at the same time, random variables over many, many, many trials have predictable patterns of behavior. That's what we studied in the last chapter. How do random variables behave? Well, if they have predictable patterns, maybe we can exploit that predictableness. Maybe when we get a sample from a population, we can still make an inference about the population. When we sample, maybe we can still take that sample data and make an inference about the population, but we have to know that our sample answer is not the answer. But maybe it's a reasonable guess of what's going on at the population level. Maybe. Well, let's take a look in this chapter about what happens, not when we take one sample from a population, but what happens when we take many, many samples from a population, and what kind of things happen with that random variable that comes out of that sampling. And we're going to do an activity today which brings up that idea. Are you guys ready to go on? Yeah? All right. So first of all, we need some new vocabulary to deal with this idea of sampling distributions. Let's define these two terms, and the terms are parameter and statistic. So, when we collect data, it matters whether we collect data from a population or a sample. When we collect data from a population, the summary numbers that we get are called parameters. But when we collect data from a sample and we try to summarize that sample with a number, the number that we get out of that is called the statistic. And that distinction is going to be very, very important. Okay. So parameter is a number that describes some characteristic of a population, and we get it by looking at everything in a population. A statistic is a number that comes from summarizing a sample. And we often use a statistic to estimate a parameter. I don't know the average weight of all the leaves on that tree in the courtyard. But I can take a sample of those leaves, measure them, and probably that sample is a reasonable guess at what I would have gotten if I had looked at every leaf on that tree. I'm not going to interview everyone at Berkeley High to find out what their feelings are on wearing hats. But if I interview 100 out of the 1,300 kids here, perhaps I get a reasonable idea of where the student body feels about whether you should or should not be able to wear a hat. Statistics are reasonable estimators of parameters, of values we would have gotten had we interviewed everyone in the population. Now, how are you going to keep these two straight? How are you going to keep straight the parameter versus the statistic? Well, they have a little thing to say, remember S and P. S for sample and statistic, P for population and parameter. So the S's go together and the P's go together. We good? All right. Now, those are the words that we use. Let's just remember that we use different symbols as well. When we're talking about a parameter, we tend to use Greek letters, except for this instance that I have on the board. Okay. When we talk about the mean of a population, we're going to use the Greek letter mu. But when we talk about a mean of a sample, we're going to use X bar or some other bar notation. Maybe Y bar, maybe Z bar. Okay. When we talk about a proportion, the proportion of Berkeley students who want to be able to wear a hat if they choose. When we talk about doing it for everyone in the population, we're going to use the letter P. But when we do it from a sample, when we only interview some of the students at Berkeley High School about their feelings about hats, we're going to use the symbol P hat. Yeah, I know. And again, the P hat symbol is the letter P, a little hat on it. Okay, so we use P for proportion, the proportion of a population. We use P hat for the proportion of a sample. You okay with those changes in notation? And whenever I use mu, I know that I'm talking about something at the population level. Whenever I use X bar, I know that I'm talking about a sample. The letters, the symbols we use are going to be really important as we go on. Does anyone require more time at this slide? Okay. Back up. You ready now? Yeah. All right, here we go. So, back again with this idea. Every time I do a sample, I may be getting a little different answer than the time before. That's expected. It's called sampling variability. But we're going to try to get our heads wrapped around this idea by asking this question. What happens if we sample multiple times? Are there any trends that pop up? Is there anything that we can use to try to make sense of that value that we got out of the sample, the statistic? Is there any way that we can look at how the statistics come out so that we have a good idea of what's going on at the population level? Well, again, what happens if we do not one sample, but sample, 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 sample? Now, typically in real life, you don't do this. But we use this as a metaphor to try to wrap our heads around what would happen if we did this. Okay? If we took multiple samples of the same size out of the population and then looked at the statistic from each of those samples, what would we get? I do a sample of 10 leaves off that tree. Find the mean. But then I take another sample of 10 leaves. Find a mean. Find another 10 leaves. Find a mean. I get X bar after X bar after X bar. And each of those X bars is an estimator of mu. Each of those statistics is an estimator of the parameter. So we're going to do a little activity, okay? And it involves poker chips. Okay? So I got a bag of poker chips here. It's really heavy too. These are really heavy poker chips. Ready? They're really heavy. I'm going to declare this bag as being a population of poker chips. All right? This isn't a sample of all poker chips. I declare this group to be a population. Right? Now what can we do? Well, first of all, I'm interested in a question. In this case, this bag has a combination of red, black, and blue poker chips. All right? And I'm interested in this question. What proportion of the poker chips in this bag are red? All right? What's that?
How many are in the bag?
There are 200 in this bag. Okay? Now, with that size of population, perhaps we could just count them out. But again, I want to get insight about what happens if we do multiple samples. So what we're going to do is I'm going to grab a handful of chips. But more precisely, I'm going to grab exactly 20 chips without looking. And I have a neat little counter here to tell me when I get up to 20, the battery box. And when I'm just over the top of the battery box, I have exactly 20.
Does that say that on the box?
No, I just did this earlier. And one more. Okay. So there's 20 poker chips. At least I think so. Perry, could you check that? Make sure there's 20 there. So there's a sample of poker chips. That's not the whole bag, right? So it's not population.
It's a sample.
It's a sample. All right? Perry, what'd you get? Did you get?
Yeah, that's right.
Okay, so he's got 20 chips. And I can ask Perry, what proportion of those chips are red?
There are 12 out of the 20.
12 out of the 20. So 12 out of 20 is, well, I'm going to call that 60%. Right? And I need a symbol that goes along with that value. It's a sample. Good. So it's going to be a statistic, not a parameter. Continue on. It's a p-hat, and it's a proportion. It's not an average. It's a proportion. Okay? So, Perry just had a sample, and the p-hat that came from that sample was 0.6. Right? Back in the bag. All right? Now, that's this bag, and this bag is for the window side of the classroom. Over here, by the way, another bag of chips. Except they're not red chips in here. They're green chips. All right? By the way, the proportion of green chips that are in that bag of 200 is the same as the proportion of red chips that are in that bag. Unknown. Because we rarely know what's going on at the population level. Yeah, it is. It's all be easier if I took your test for you. And then on the AP exam, I'll just take all your tests on the AP exam.
Rip that boy.
Oh, by the way, did you hear about that big controversy in
Syracuse?
No. It's actually in New York, but not the Syracuse. There was actually a cheating scandal at one of the really high-end high schools in Long Island, New York, where people were taking the ACTs and the SATs for other people. Yeah, well, this time they got caught. And it's a big scandal. All right, so here's the idea. Yeah. All right, so we're going to do, for each pair of person, for each desk, in fact, Megan, why don't you move up, I want you to move, so I want you all in pairs. Okay, and what's going to happen is that we're going to do repeated draws, repeated samples from these two populations, and then we're going to find out what do all those p-hats look like. All right? So what I want to do is I'm actually going to stop this recording because no one's going to want to listen to a recording of you guys doing samples. All right?